Today we're going to talk about synthesis again, and we are going to go in detail on the synthesis for any type of articulated system, including the tree structures, which are the ones that are more complex right now. We will pass over the ones that have loops kind of, on our toes. So we will just see briefly what we will do for in this case, how we will approximate those to serial chains. Okay. So let's just call this kinematic synthesis. For general articulated systems. Okay. And we already talked enough about the task and how to define the task, and that is, this thing is annoying, and that is not going to change much. Well. So let's start with talking about the structure of that we are going to use. So basically, remember that we can always represent any articulated system with a rooted graph. And that is going to be important in order to calculate some of the parameters for the exact synthesis. So let me just put an example that I have here. Okay, let's see. This is just a random case. Okay, one. RPSSRR. Okay. So there is a possible graph RPSSSRR. So now we need to be able to identify this, and we can name the vertices 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the way. Oh, sorry, 5, 6. Yeah, that's correct. So remember, what we have here is that the vertices correspond to the links. A vertex is equal to a link. So it's our physical part from one joint to the other. The edges represent the joints, and we need to state what type of joint we have, and that's what this letter corresponds to. So these are revolute, prismatic, spherical, 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 revolute, revolute, and revolute joint. Then we have this particular vertex, which this is the root vertex, and that corresponds to the ground, the one that is fixed in the ground. So this basically sets our reference frame. So this is the ground. So this sets fixed reference frame. Sets the fixed reference frame. And then we have this, these are just normal links in our system. And then we have these ones with the square, and those are the end effector links. End effectors. Normally we only have one end effector, but in the systems that we study, which are the systems with a tree structure, in that case we have several end effectors. So there is a graph with a set of vertices, a set of edges, V, which is the number of vertices, is equal to 9. E, that is the number of edges, is equal to 1, 2, 3, 4, 5, 6, 7, 8. So what this corresponds to a physical system in which we have a fixed reference frame. Okay, and this is a body that is, together with number 1, and then we have a revolute joint that is, is joining the ground to link 2, and then we have an aprismatic joint, so this will be R, P, and then we have 3 here, right? S, S, S. Okay, let me just put as these are spherical joints, let me just put this symbol S, 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 and then we have another body, we have a revolute joint, and here we have end effector with its reference frame number 5, and here we have directly and then the effector, which is number 6, and here we have one revolute joint, another revolute joint, and the last end effector, which is number 9. So this is the kind of like the kinematic sketch of that system, and this is actually attached to the ground if you want. We will put some lines there. So if we are interested in design or even in path planning or in control, we will be given the coordinates of these end effector frames with respect to the fixed frame, right? So we are going to call those P5, P6, P9. Those are the transformations from this frame to that frame. So for instance, this over here is what we are going to call P9. And let me just take a different color with that. This one over here is P9. I'm going to spoil all my drawing. This is P5, and here we have P6, right? Now sometimes it is interesting to change what is your reference frame. So you may change one end effector for the ground. Sometimes it's interesting as a methodology to solve problems, sometimes maybe interesting just to, from your physical problem. But in the case of these structures with several end effectors, we will need to do that. So let's see how we do that. Now we want to have this as the fixed one. So imagine now we fix this end effector and we see how the whole chain moves when this is fixed. So now we need to express the motion of all these 3 as a function of that, which means we need to compute this. I'm going to call this P5 asterisk, P6 asterisk, and P9 asterisk. Now we want to have these transformations with respect to this reference frame, for instance. So what if we fix end effector 9 as the ground? If we fix end effector 9 as the ground, means we are measuring from frame 9 from frame 9. Okay, so let me just put it here, just to complete this messy screen. How are we going to measure from frame 9? Well, we can create this. So notice that if you want to create P5, you can create that as the composition of P9 plus this P5 star, right? So we have, notice, and I don't have colors here, but the ones that are star are measured in 9 frame, the ones that don't have star are measured in 1 frame, okay? So we have P5, we can create that as the product of transformations, and that will be P9 times P5 star. So if we want to compute P5 star, we can just pre-multiply times the inverse of P9. P5 star will be equal to P9 inverse P5. That's the way we change the reference frame that we measure from. We pre-multiply by the inverse of the transformation to that frame. Same thing is true for P6. P9 inverse P6. We can even apply it to itself. What is the transformation from 9 to 9 with respect to 9, right? So P9 is equal to P9 inverse P9, which is the identity, which means, yes, I am measuring from myself. And you can even calculate what is now this, which will be an end effector now, okay? So P1 will be equal to P9 inverse times the identity. You know, the motion from 1 to 1 with respect to 1 was the identity. So this is just P9 inverse, which is, you know, it's just this inverse transformation. So when you only have one end effector, this is a trivial operation. Just do the inverse. When you have more than one end effector, then you need to do this two-step process.
And which one is P1 star?
So one is this one. So now this end effector, this will be an end effector with respect to the blue. So this will be our end effector now. And this frame will be moving. So this is frame 1 because it corresponds to body 1. Okay?
So if we want to go to the end vector, we will P9.
So now, you are measuring from here now.
Yes.
And now you want to know how this one is moving. That will be P6 star. How this one is moving will be P5 star. And how this one is moving will be P9 star, which is the same as the inverse of this one.
Okay.
Okay. So what we have done is we have done this graph now. We have changed this to, this is a square, and this is our ground now. All right. So now 9 is our ground, and then 6, 5, and 1 are the end effectors.
Sorry, the low blue line should be P1 is though.
Where are we? Oh, sorry. Yes, this is not P9. You are right. Probably that's what Kutaiba was confused about. Yeah, P9 will be, you know, going to itself, right? P9 star. Right. Yeah, that's P1 star. You are completely right. So this is the change of ground link. And now is when we erase this and we continue. So somebody has to take the picture of that. So we have the rooted tree graph, and then we have the change of n effector, so we know how to do that. Now let's do the next step, which is the contraction of the graph. Contracted graph. And I'm going to put the same example because we'll use that, I think, for the contraction. Let's just do that one, and then we will do some other. So this was our example. 1, 2, 3, one more, and two more, right? We had R, P, S, 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 R, R, R. 1, 2, 3, 4, 5, 6, 7, 8, 9 is our easy way of. All right. So contraction, and we are going to contract graphs with no loops, okay? So now this consists of eliminating, I'm not sure if, let me just say, I cannot change what I say too much, right? Oh, this works better. So each serial chain is transformed into one edge. Okay? So every segment that is just a serial chain, we will transform that in a single edge. So basically we are eliminating the binary links. Okay? Binary, remember, means that they are connected to two edges only. So for instance, for this one, in this case we will have one. Here we have, this is a serial chain, it's an RP chain, which means we will create a single edge there, and we will call that the RP. We still need to identify what we have there. This link is binary. This one is not binary. This vertex. 1, 2, 3, 4. Degree 4, right? So we need to leave that. Now here we have another serial chain. It's an SR chain. So this one over here, SR. This one is just an S chain. And here we have an SRR serial chain. So that gets transformed into a single edge, SRR. And this was, let me just skip the notation. So 1, 3, 5, so that we identify them. We won't use this notation, but okay, so notice that there are several things that happen is that we don't have any binary link anymore. And then another thing that happens is that the links of degree 1 is either the root or an end effector, which means we don't need to identify the end effectors with a box anymore. If it's not the root, then it's an end effector, if it's a link of degree 1. We can do that if we don't have loops, okay? So this is the process for, we can do the same process for graphs with loops, but for a graph with no loops, after this contraction, if we didn't have loops at the beginning, then we won't have loops at the end, obviously. What we will have is no binary vertices. And then another characteristic is that the relation between the number of the vertices and the number of the edges. 1, 2, 3, 4, 5, 1, 2, 3, 4. The number of vertices is equal to the number of edges plus 1. And then the only vertices of degree 1 are either root or end effectors. And then there is another characteristic because we don't have loops. That's not because of the reduction. Is that there is a single path to go to a given end effector. A single path from root to each end effector. Now, as I said, we are assuming that we don't have loops, and that's something we accomplish in a different step, and we will talk about that maybe next day. But basically this is our contracted graph, and that's pretty much all that we need to say. So once we have it in this form, we can write the forward kinematics for this. So let's talk about the forward kinematics. And we have seen already that we can do the absolute forward kinematics, or we can do the relative forward kinematics, and usually we will just write the relative forward kinematics, and just remember that multiplying by the transformation to the reference configuration, then you get the absolute one, right? So the forward kinematics, and let me just use my same notation here, which is the same that we use in our papers. What we need to do when we have more than one end effector is we need to write one forward kinematics equation for each end effector, because what you want is the set of positions and orientations of the end effector, right? So you will need one different one for each end effector. Need to write one forward kinematics equation for each end effector. So in this case up here we'll need 3 sets of forward kinematics equations. So let's say that for a system with B end effectors, which means with B branches, B end effectors. At the end of each branch, after we do the reduction, we should have one end effector. Sorry, after we do the contraction, the contraction and the reduction, we should have an end effector. And we haven't talked about the reduction, but it's to eliminate the loops. Okay, so for a system with B branches, we can write these forward kinematics equations, and we will call that Q sub I hat, and that means we are going to write them in dual quaternions, but it doesn't matter, of delta theta arrow, which means this here we have all the joint variables, and that is going to be the product from okay, let me see which symbol I use. J equal 1 to K sub I of the exponential delta theta I, theta j divided by 2 Sj, alright, times the product J equal Ki plus 1 to Ni of the exponential delta theta Ij hat divided by 2 Sij. I equal 1 to B. So that's 1 for each branch. And now let me explain this notation. So this part over here corresponds to common joints. And this part over here are the ones that corresponds joints that appear only in the branch I. Okay. I joins. I'm going to just go slowly through the whole notation here. So what we are saying is for branch here, what we are saying is branch I has Ki common joints common to other branches, and a total of Ni joints, counting the common joints, total joints. Okay. So first we multiply the common ones and then we multiply the rest. Now remember what this means is the product, of course. Every one of these is the screw transformation about one axis, okay, just as a recall. This exponential notation is not associated with a particular algebra, and we haven't studied this in detail, and we probably need to do it, but delta theta j divided by 2 sj is the screw displacement about joint Sj, and these are the Plucker coordinates of the joint. Put whether it is in a matrix form or in a dual quaternion form. Screws joint Sj, and the joint variables will be delta theta. So let me just say that theta j is the dual joint variable So this will be the general case in which we may have rotation and translation. We group both of them with the dual part. So theta j hat could be, for instance, theta j plus epsilon tj. And if you don't have translation, if it's just a revolute joint, then you eliminate this part. If it's just a rotation, you eliminate the dual part. If it's just a translation, then you eliminate the rotation part. If it's a cylindrical joint that can rotate and translate, then you need to leave both there. So are you curious about this? Have we done this?
No. You've seen this thing in Yumi's papers. The flex.
Okay. So do you want to know where this comes from? Yes? Okay, so we will do one core class on this, okay? On getting this to understand why the exponential of something gives you the screw displacement. And it's a nice theory, but it's kind of involved. All right, so assuming, and you can just think of this as the transformation, the screw rotation about the axis, and just think of this as notation. This is a simple screw rotation, and you multiply the screw rotation about the axis, you get the total transformation of the chain.
Well, I think in your notes also, or in the
It's in chapter, I think it's chapter 3 or 4 of the book. Yeah, there's a chapter on Lie algebras. That's where this appears. But it's related to the screw displacement is exactly that. Yeah, right? Is the rotation about a joint and then the translation about that same joint, right? And this is one of the possible ways of expressing that screw displacement. Okay. So just think of it as notation. So you have screw displacement about the product of screw displacements along the joints, okay? And let me see what else I need. And then we have this delta theta. When we put delta theta instead of theta, what we mean is these are the relative forward kinematics, which means we go from a reference configuration to the next one. So the notation delta theta means theta j position P1 minus theta j at position, let me say position, see a letter that I haven't used. So for instance, okay, 1. Okay. So what this means is that the angle at the first position that you are considering may not be 0. Usually if we start from the reference configuration from the manufacturer of the robot, then the angles are equal to 0 and we move from there. But now if you are here and you want to move from here to there, this angle is not 0. So this relative angle is just the subtracting the absolute angles, okay? So this is just relative angles or relative joint variables. joint variables with respect to reference configuration. And because we are doing relative forward kinematics, we will always have a reference configuration that we move from. Reference configuration. Okay. Big notation, but we will practice. Okay. This, this big thing summarized is you take your, the rotation about or the translation about each of your joints and you multiply it together. And some of those joints will be common, and some of those joints will be uniquely from your branch. Let me do one example, maybe. Example. Okay, let me look at the example I have here, and this is where our hand designs start becoming interesting. So this is already a compacted graph. 2R, 3R, R, 2R, 2R, 2R. So all the branches don't have to start from the same point. Now this gives, this yields very interesting hands also, that you may have a finger right here interacting with your fingers here, okay? So let's take this one, and let's just identify stuff in here. So how many branches we have? As many as in the vector, so 4 branches. B equal 4 branches. And now let's identify how many common joints and how many total joints each branch has. So that will give us our number. So for I equal 1, B1 has, how many common joints are, let me just give names to that. Even, okay, so I started here, I think. 1, 2, 3, 4, okay? These are the number of the branch. So how many common joints does branch 1 has? Common joints in this branch. 2. That means the ones that are shared with other branches. So 2. So that's K1. K1 equal 2 common joints, and then the total number of joints in the branch is 5. N1 equal 5.
Which one are in common? The 2R and the R?
These 2 are. So this means there are 2 revolute joints there. So those.
Yes, but they are common with the ground or?
No, that means that that they are shared with other branches. So you see these 3 revolute joints here, they will only move this and the vector. However, if you move a branch here, you will move this one and the rest of them. So that's what we mean by common, that their motion affects, all those. So in this case it's 2, it's not 3 because this doesn't affect this one. Right? So I equal 2, B2 has K2. Now how many common branches are, this is 3. Yeah, 3, because you have these 2 and this one. If this moves, they are not going to affect this one, but if that moves, will affect common. And then N2 total will be 1, 2, 3, 4, 5. Same thing, yeah. Total. And we can do the same thing. So we have for B3 we have K3 equal 3 is the same number. N3 equal 5. And B4 will have K4 equal 3 and 4 equal 5. Now let's write the kinematics equations of at least one of them, just for, remember we will have to have 4 sets of kinematics equations. Each of the sets is a whole transformation, so it has either 8 components if you use quaternions or 12 components if you use homogeneous matrix. Okay. All right, so let's just do forward kinematics equations for branch. Let's just do branch 1. So Q, I forgot my notation already. Q1 of delta theta. Q1 of delta theta. Maybe I should do the drawing of the actual system just to give it a little bit of S1, S2, and here we have one branch that goes over here, and we have here 1, 2, 3 joints, right? And then one end effector, and this is what we call branch 1. And here we have this one. Okay, where am I? And from here we have 3 more, right? 1, 2, 1. Let me know if this drawing doesn't make sense. 1, 2. Yeah, that connects one that is ternary to one that is degree 4, right? Okay. So this is the monster that we are looking at. Now the notation used in that formula is quite nice. It identifies the branch as well as, you know, the joint within your branch. So let's use the same notation that we use here. So we will have the product of the common ones. So we will have, you know, the exponential of delta theta 1 over 2, and we are going to take the hat out because this is just a rotation, it's a revolute joint, so it's just a rotation. S1, that's the screw displacement about the first one, the exponential of delta theta 2 over 2, S2. Those are the common ones. And now if you look at your notation, the axis is written such that the first subindex corresponds to the branch, and then we count for the joint continuing from the one that we left there. Okay, so we'll have the exponential of delta theta. Now we are in branch 1, so that will be 1, 3 S 1, 3. Okay, so it's the third joint if you are counting towards branch 1. Times the exponential of delta theta 1, 4 S 1, 4 exponential of delta oh sorry, I forgot the 2. Don't forget the 2. Theta 1, 5 over 2 S 1, 5. All right. Let me do one more branch because this example I think it shows the notation very nicely. So S1, so this one will be S13 because this is branch 1. So this one is S13, this is S14, and this is S15. Now let's go to the second branch. Forward kinematics equations, branch 2. I'll try to write it right in line so that you guys can see in the back. And these are the ones that correspond to B1. Okay. For kinematics equations for branch 2, Q2 of delta theta arrow equal to common ones. Now we have 3 common ones. Okay, and we are going to call this one S3 because it's a common. Okay? So we'll have E delta theta 1 over 2 S1, E delta theta 2 over 2 S2, E delta theta 3 over 2 S3. These are the common. And now we will continue. This is one over here is branch 2. Now we will name them as branch and then continuing from the last common one. So this one will be S23. S corresponding to branch 2, 24. Delta theta branch 2 joint 4, because we had an S3. S24. And exponential delta theta 25 over 2 S25. Okay? So branch 2 joint 4 and branch 2 joint 5. That allows us to, looking at the last number here, know how many joints you have in each branch, and it allows you to identify which ones are common and which ones belong to a given branch.
Can you repeat the last one? Yes. Starting from,
So we always have to start from the fixed joint, right? So we have the rotation about S1, the rotation about S2, and the rotation about S3. These are the common ones.
Alright.
And then you continue towards branch 2. The rotation about 2,4 and the rotation about 2,5. That means branch 2 joint 4 has to be the next after 3. So you continue from the last one you have here. The next joint will be 4. Sorry, this is wrong. This is 2,4. The next one will be 4 and the next one will be 5. Okay. So
why
one
is it S3, why is it not S2, like S13, S14, S15?
because this is a common joint.
Okay.
It's common to all these branches. So that comes here. K equal to 3 are common. So all the common ones will have a single name. And then the ones that only belong to a branch will have the name of that branch. And it doesn't look very intuitive, but it's a very good way to identify where the joints are.
All those ones which are common are...
You have a single index. Okay? And the ones that belong to a branch, then they have double subindex. Branch and then, keep counting from the last common joint, basically. So far it has worked nicely, this notation. But we may find that we are cases in which we said, no, this is not working. If we do, just let us know, because we are here for designing crazy stuff. All right, so we have the forward kinematic.